by using the coordinate basis method, where you are going to solve a differential equation, and the other is what you generally call a matrix method or an operator method, where you define creation and annihilation operators. What was the method that you already know?
Sir, by the operator method, you meant the using ladder operator, right?
Yeah.
Sir, actually, both were done, but it was done in a very rushed manner. So, for me, ladder operator is pretty much clear, but for the other part, it is not very clear for me. I don't know if it is the same situation for everyone.
Yeah. So maybe one or two more can speak up so that we can decide what to do. Ashwati? Arshad?
Hello, sir. Yes, sir.
Yeah. So what do you say?
Sir, we were taught that ladder method,
Hmm.
and I don't know what to say.
So we should do then the other method, which is generally called an analytic method.
Okay, sir. It's up to
Yes,
you.
sir. Yes, sir.
Sir, I remembered one more question about CSI and there was a question like there was a liquid, sir, on which capacitor, parallel plate capacitor.
We'll discuss at the end.
Okay, sir.
Okay. Can you see the screen?
Yes, sir.
Okay. So let us discuss today the one-dimensional harmonic oscillator. So the Hamiltonian for the system is given by E square by 2m plus half m omega square into. This is the Hamiltonian of the system. So we are going to look at Schrodinger equation. In that is, we would like to solve H operator on some psi of x is equal to E psi of x. This is the equation that we would like to solve. And of course, we are going to do it in coordinate basis. So in coordinate basis, the operator x operating on any function of x will be simply x multiplied by f of x, and operator p acting on any function of x is equal to h bar divided by I into d by dx operating on f of x. So this is how these two operators are defined. And then our h psi equal to E psi will be an equation like this: minus h bar square by 2m into d square psi by dx square. This is p square by 2m plus half m omega square x square into psi is equal to p. So this is what you call as time independent Schrodinger equation, or it's a statement of an eigenvalue property. Okay. So you can in the first step, what we will do is we will try to recast this equation. So recast the above equation in terms of dimensionless variables. This is something sometimes we call as non-dimensionalizing of the equation. And this is very general technique which is used in, in many differential equations. So for that, what I will do is that I have this x, which has got dimension of position. So I will try to write this in terms of some length L, and this is, let me call it as psi. This is a dimensionless. So this is dimensionless. So this is dimension. That means there is some. So here, what this L is some kind of a characteristic length scales of the system. In this case, the system is one-dimensional harmonic oscillator. And if I know that this characteristic length scale, then all lengths can be measured in units of this. That is, then that becomes simply dimensional. And I can also say that I have energy, and let me say that there is also a characteristic energy such that this becomes an epsilon, and this epsilon is also dimensional. So I want to recast this equation in terms of these dimensionless variables, psi and epsilon. And note here that we don't know what L and E naught are. We are only saying that, so this E naught is kind of a characteristic energy scale of the system, so that all energies can be measured in terms of this E naught. So in doing this dimension, this technique what I am going to present now is a very general technique. It can be used for any general differential equation. So I'm going to ask what is d dx. So that is nothing but d psi into d psi dx. This is chain rule. And d psi dx is actually 1 over L. So this is equal to 1 over L d psi. Okay, so L is some constant which we have to determine. So I substitute this one, then this equation can be written as minus h bar square by 2m into 1 by L square into d square psi by d xi square. Now psi will be a function of xi, okay, plus half m omega square. Now x square I will write it as L square psi square into psi is equal to, I must write this as epsilon E naught into psi. So this is the equation. So this is the equation in terms of this variable. Now this equation is, we have to simplify this equation. What I will do is, I will write this, I will multiply the equation throughout with minus twice ml square by h bar square. Then I will have 2 will cancel, and I will have m minus m square omega square L to the power 4 divided by h bar square into chi square into psi is equal to minus twice m L square into E naught divided by h bar square into epsilon into psi. Now, once you have an equation like this, we remember that L and E naught have to be determined. Okay, so we have to determine L and E naught. How do you determine this L and E naught? You can determine this L and E naught in the following way. So let's say that you have this equation. In this equation, let's determine L such that this coefficient is made 1. Okay. That means, what is our L now? L is equal to square root of h bar by m omega. If I choose L like this, h bar by m omega, then h square is equal to L square is h by m omega, or L to the power 4 is h square by m square omega square. So this coefficient is equal to. So this is our characteristic length. Okay. Now you have to determine your E naught. Now how do you determine this E naught? You determine this E naught by setting this coefficient is equal to 1. I don't want in my equation anything other than these dimensionless variables. Okay. So if I do that, then I will have this coefficient is equal to 1. That means twice m by h bar square into, already I know what is L square. L square is h bar divided by m omega into E naught is equal to 1. So this m will cancel and one h bar will cancel. So it is 2 E naught by h bar omega, 2 E naught by h bar omega is equal to 1, which implies your E naught is equal to h bar omega by 2. And if you can recall, this is the ground state energy, and this is the characteristic. So we are now successful in determining the characteristic length scale of the system, which is given by square root of h bar by m omega. You can see that m and omega are the parameters of this system. M is the mass of your particle and omega is its angular frequency. H bar is a fundamental constant. So you can see that this one is in terms of characteristic properties of the system. So characteristic energy is given by h bar omega by 2. So with this choice, we are now able to write down in terms of the dimensionless variables. Okay, so in terms of dimensionless variables. We have the time independent Schrodinger equation. So I can take this epsilon into psi to the left hand side and write this as d square psi by d psi square plus epsilon minus psi square psi is equal to 0. So this is the equation that we have to solve. So in terms of dimensionless variables, we have this equation. Now you can ask a question that which is the second order differential equation, but it's not very easy to solve this equation as such. So first what we will do is we will look at in the second step, we will look at so the asymptotic form of the solution. Asymptotic form of psi of z. That is psi of xi as xi goes to plus or minus infinity. Okay. So there is a general general boundary condition. Okay. So note that V of x, the potential, goes to infinity as x goes to plus minus infinity. Okay. So as a result, psi of x and xi are same because x is linearly related to psi. Psi of x must go to 0 as x goes to plus or minus infinity is the boundary condition. Boundary condition on psi of x, which is also true as it is psi of xi. But then how does it go to 0 is something that we have to understand. That means what is the asymptotic form? There are several functions which will go to 0 as x goes to plus minus infinity. And like what function this psi will go to 0 as x goes to plus minus infinity is what we have to understand. Now, for large psi, okay, so for large psi, we can write the above differential equation as p square. So let me call this as some psi tilde because the solution is not same as psi, something else. Okay, and I can neglect epsilon, and I have minus psi square into psi tilde is equal. Because epsilon is a fixed value, and xi is so large that epsilon can be neglected. So this is the equation that we have. That means d square psi by d psi square is equal to psi square into psi. Okay, so we have to ask a question: what kind of solution this has? For example, one can guess that, so we can guess psi tilde of psi to be e to the power plus or minus xi square by 2. Okay, e to the plus or minus xi square by 2. So let us look at what happens to psi tilde prime of psi. That is equal to e to the power plus minus xi square by 2. And you have plus minus xi. Right? So that is what will be your 2 xi, but there is a 2 in the denominator, so that will be it. Now you ask what is psi tilde double prime of psi. This will have 2 terms. So first one is I do a differentiation of this. Okay, so that will give me plus minus 1. Plus minus 1. And then I do a differentiation of this again. That will give you a plus minus psi. So which will become xi square, right? So plus xi square into e to the power plus minus xi square by 2. Okay. Now, since xi is large, okay, since xi is large, you can write this as xi square into psi tilde x. Okay, one you can neglect because xi is tending to infinity. So this is psi double prime is equal to xi square into psi is this equation. Now, this guess has allowed us to write that the psi tilde of x, psi tilde of psi can be written as some kind of constant a into e to the power psi square by 2, because these are two solutions, both satisfy this, plus b into e to the power minus psi square by 2. Okay, but our boundary condition, that the psi of xi should go to 0 as xi goes to plus minus infinity. Okay, demands the choice a should be equal to 0, because if this function is there, then the wave function will diverge. So it cannot diverge. So I should take a to be equal to 0. So my psi tilde of xi is equal to some constant e into e to the power minus xi square by 2. Okay, so this is the asymptotic form of the solution. Now, yes.
So in the very beginning, how did you guess that function? Like from what form did you guess that function e to the power plus minus psi square by 2?
How do we guess? Most of the times in differential equations, you have to make some guess, right?
So is there any special form for that? Like for that?
Well, see, this is a differential equation with what is called variable coefficients, right?
Yes, sir.
Differential equation with variable coefficients. So, okay. So let me come back to this question, because if you don't want to guess and try to do something from the first principles, then we have to go back to these methods of differential equation. Okay. So let's not let's not deviate too much into that now. Let's
Okay,
say
sir.
that we will be able to guess, and if you are not able to guess what to do, we will think about it later. So what we are doing is here we are guessing and then verifying. If your verification shows that this is not a solution, then you go back and do another guess. And this is an official procedure of solving differential equations.
Okay, sir.
So this is the asymptotic form, and this satisfies this boundary condition. Now we have to, in the third step, what we will do is that so we write, so our psi of xi, okay, so we can write the psi of xi, that is the solution of the Schrodinger equation in the dimensionless variables. We can write this as some constant, which you can call it as some a or whatever. This a is not that a. Let's call it as some b into e to the minus xi square by 2 into some function of xi. Now we are writing it like this so that this function dominates as xi goes to plus minus infinity, and this function dominates for finite xi. Okay, so that is the idea. So we do not know what this function is, but at least a part of the wave function we are able to carve out in the sense that for large values of xi, this is going to be the form in which it exists. So we have this f of xi written in this fashion, and now we can write. So what we are going to do is that by substituting this, in Schrodinger equation, we get a differential equation for the function f of z. Okay, so you get a differential equation, and you have to solve that differential equation to find what is f of z. So remember, our equation is d square psi by d psi square plus epsilon minus xi square into psi is equal to 0. This is the equation. So to substitute this in this, I know this is psi. I must now write down what is psi prime of xi. So that is equal to, I can write down e to the minus xi square by 2 into f prime of xi minus psi into f of xi. Because this is two functions, is a product. There is a b sitting here, doesn't matter. And psi double prime of psi is equal to b into, I have to differentiate this and differentiate this, and this, when I'm differentiating this, I have to once again use a product rule here. Okay, so if I do that, I have minus xi square by 2, and when I do this differentiation of this, I get a minus xi here and xi square here, and when I do a differentiation of this, I will have minus xi f prime. So so I have something like xi square into f of xi minus 2 times psi into f prime of psi, okay, plus f double prime of psi. This is what I will have. Okay, so if I substitute this in this equation, substituting this in this equation, so I will have b e to the minus xi square by 2 into f double prime of psi minus 2 xi f prime of psi plus xi square into f of xi. This is this term, that is psi double prime. Okay. Plus epsilon minus xi square into b e to the minus xi square by 2 into f of xi is equal to 0. This is psi. So now you can see that this b into e to the minus xi square by 2 is there in both the terms, which is not 0, and hence that that part can be pulled out, and then remaining part is equal to 0. And notice that there is plus xi square into f of xi and minus xi square into f of xi. So this term will actually cancel with this term. So I have an equation. So the differential equation satisfied by the function f of psi is f double prime of psi minus 2 xi into f prime of psi plus
The epsilon into f of xi.
epsilon into f of xi, but I think I have some epsilon minus xi squared. Okay, so let me just see if I have done this correctly. My psi double prime of psi is equal to b e to the minus xi square by 2 into minus xi into f prime minus psi f plus b e to the minus xi square by 2 into f double prime minus f of xi minus xi into f prime. Okay, so you can see that there is one term which is called minus f of xi, which I have missed here. So you will have minus f of xi. So that means here I have an additional term called minus f of xi. So that gives me that plus epsilon minus 1 into f of xi is equal to 0. So this is the equation, that differential equation satisfied by the function f. So notice that this is a second order differential equation, second order ordinary differential equation with variable coefficient. Okay. This is fine, because this is an equation where every point between minus infinity plus infinity is is an ordinary point. So you can solve this by using the power series method. So the solution of this one, okay, using power series method. So for that, what we will do is, let's assume that this f of psi is equal to sum over k is equal to 0 to infinity to have some aj into psi to the power. Let's assume that a power series solution like this, we have to now find out aj. Okay, so this is something which is easy. I'm sure you have done this in many mathematical physics course, in quantum mechanics course, etc. So what we have to do is we substitute this in this equation. So your f of psi, f prime of psi, is equal to sum over j is equal to 0 to infinity aj into j to psi to the power j minus. And f double prime of psi is equal to sum over j equal to 0 to infinity aj j into j minus 1 into psi to the power j minus. So we are going to substitute this in this equation. So I have sum over j is equal to 0 to infinity aj j into j minus 1 into psi to the power j minus 2. Okay. And minus 2 times j is equal to 0 to infinity, j equal to 0 to infinity, aj into j, and I will have xi to the power j, because in the first derivative I have xi to the j minus 1, this term, but then there is one xi sitting here outside, so when I take it inside, it will be simply xi to the j plus epsilon minus 1 into sum over j is equal to 0 to infinity aj psi to the j. That's equal to 0. Now notice that in the first term, okay, if I take j equal to 0, okay, because of this coefficient j sitting here, this term will be 0. If I take j equal to 1, because of this term, this will be 0. So even though I have j is equal to 0 to infinity, the first two terms are 0 in this. So this is as good as writing j is equal to 2 to infinity. You follow? J equal to 2 to infinity, because j equal to 0. Okay, so note that j equal to 0 and j equal to 1 terms are 0 because of the presence of j and j minus 1 here. So this is written as j is equal to 2. Okay, so now this writing it as j equal to 2 is helping us in the following fashion. Suppose now I write, so let's say j minus 2, you write it as some m. Okay, this implies your j is equal to m plus 2. Okay, m plus 2. Now, if j is starting from 2 to infinity, okay, so j is equal to 2 to infinity. It implies m is equal to 0 to infinity. Okay. Now, this term, okay, so the first term or first sum can be written as sum over m is equal to 0 to infinity. Okay, what is j? J is m plus 2. So I have a m plus 2 and m plus 2 into m plus 1 into xi to the power m. Remember, this m is just a dummy index because m is running from 0 to infinity. So I could rewrite this equation. Instead of m, I can as well call that as j itself. Okay. So only thing is, see that now it is xi to the power m. So since m is a dummy index, since m is a dummy index, we can call it j as well. So when you do that, you have an equation like this. Sum over j is equal to 0 to infinity. This is common to all the terms. Okay. And I have psi to the power j, that is also common to all the terms. And I have the coefficients, which is aj plus 2 into j plus 1 into j plus 2, that is from the first term, minus 2 times j aj plus epsilon minus 1 times aj. Okay, so that is equal to 0.
Sir, for this
Yeah.
case, similarly for the second term, shouldn't it be from j equal to 1 to infinity, and it should be aj plus 1 into j plus 1 for the middle term?
Yeah, that's right. But what I'm saying is that I don't want to do that like that. Okay, it is going to be 0 first term, but let it be there like that. Because why I am doing this only to the second term? Because I want to make this xi to the power j minus 1, j minus 2 as xi to the power j, so that I can take this common.
Okay, sir.
I can take this common. So now this coefficient has to be 0 for every j. Okay, because this 1 xi square, these are all monomials which are linearly independent, and coefficient of term by term should be equal to 0. Okay, so that is coefficient of xi to the power j should be equal to 0 for every j. Okay, so that means now I have a recurrence relation between aj plus 2 and aj. So I can write down aj plus 2 is equal to, so let's take this on the other side. So twice j minus epsilon minus 1 divided by j plus 1 into j plus 2 into aj. So this is a recurrence relation that we have for this power series. That means if A naught is not equal to 0, okay, then this non-zero value of A0 will give you A2, A4, A6, etc. Can be obtained. So I require only one constant, that somebody has to supply me this A0. If somebody is supplying me A0, all even, the coefficients of even powers can be obtained. In the same way, if somebody gives me A1, so if A1 is not equal to 0, then A3, A5, A7, etc. can be obtained. So as you can see that any second order differential equation will require the knowledge of two initial conditions or two conditions. So those two conditions are A0 and A1. So this one has to supply from the physics of the problem. And once you give me these coefficients, then this recurrence relation will give me all the other coefficients. Okay, so that is what is given by this recurrence relation. This is a 2-point recurrence relation because Aj plus 2 is related to Aj. So since there is a step of 2, I require A0 and A1. Then all other coefficients can be determined. Okay, so that is one thing. And the second thing is that we would like to understand what happens to, so how many terms should I have? Should I have all the infinite terms? Okay, so that we will once again look at what is called, so let's try to look at asymptotic analysis. Okay, so let's look at, let's say this is our fifth step. So asymptotic behavior of f of z. Okay. Now f of z is given by this power series. Okay, so note that f of z is equal to sum over j equal to 0 to infinity aj into psi to the j. Okay, and if you are given a0 and a1, then you can use this recurrence relation to get all other coefficients. Okay, so now note that as j goes to infinity, that means as you go to higher and higher terms of this series, the above recursion relation, relation can be written as so if j is going to infinity, what happens is that your epsilon minus 1 can be neglected, j plus 1 can be written as j plus 2 can be written as j. So you will write this aj plus 2 is equal to 2 by j into aj. Okay, aj plus 2 can be written as 2 by j into aj. Now this is something which so this is true, of course, only if j is very large. Okay. Now what happens if this kind of a recursion relation is there? Now you can see that your so in this limit, in this limit, what happens is that your a let us say your a2 is like Okay, so let us see that you can see that your A2 will be written as 2 by so that means this is, okay, let us call this as A4. Okay, that means j equal to 2. So 2 by 1, j equal to 2, that means it is 2 by 2 into A2. Okay, similarly, if you want A6, it is 2 by okay, if I give A2 here, I get A4. If I put A4 here, I get A6, right? So that means it is 2 by 4 into A4, or that can be written as 2 by 4 into 2 by 2 into A2, and so on. So you can see that if you are looking at let's say A8, let me write one more time, which is 2 by 6 into A6, which is equal to 2 cube divided by 6, 4, 2 into 8, and so on. So one can write this a general term in the following fashion. Okay, so you can see that I can write this as, I can pull out 2 from here, 2 from here, 2 from here, then this becomes 3 factorial. So this can also be written as 2 cube divided by what is called, there is a 2 cube coming from here and a factorial 3 coming. Okay, so now if I want to write, this is 4. So if you have A to N, I can in general write something like A to J can be written as 1 by J factorial. Okay, 1 by J factorial into some constant, which I may call it as an A naught or something. So you can see that okay, so this means that if you are trying to write you remember that the f of xi can be written as
Excuse me, sir.
A0. Yeah.
Won't it be 1 by j minus 1 factorial?
What would be? No, that. Yeah. So let me just write it here. So let's say I have A2 xi square plus A3 xi cube plus etc. This is the infinite series that we are talking about. Okay. Now this recurrence relation will tell you that if I know A2, I can find out A2, and if I know A2, I can find out A4, and so on. Similarly, A1 to A3, we can find out like that, right? Now, what I'm trying to say is that this is an infinite series, remember. So I'm going to write this as a large number of terms I will write here, okay, plus let's say I have some xi to the power some very large value, let's say some n, and if I pull that out, then I will have an plus 1 into xi plus an plus 2 into xi square, etc. This will be an infinite series, correct? Now this is so this line that I have drawn here corresponds to series before n up to n. Okay, so n is very large. Okay, now what I'm trying to say is that in general, the recurrence relation that we have talked about, this recurrence relation okay, let me just show that. This recurrence relation that we have talked about is in general true for any. So this is true for any j. Okay, this is true for any j. But then when you leave out some members and then write this one, so if you consider this kind of a series, okay, for this series the recurrence relation can be written as aj plus 2 is equal to 2 by j into aj. You follow? So this recurrence relation is valid for an infinite series which is a later part of the series. After you remove several terms, a large number of terms, and then the remaining series also will be like that. So that is the asymptotic recurrence relation that we are talking about. Now, if this is the recurrence relation, what will be this infinite series? That is what we are trying to understand. Now, if you want to understand that, so this can be written. This can be written as we have seen. That's for example, if so, if you want to write down. So let's say this we can write it in the following fashion. Let's say j is equal to 0 to infinity. Okay, so I have a to j into psi to the power 2j divided by a to j into psi to the power 2j. But then our a to j is simply written as sum over j is equal to 0 to infinity 1 by j factorial, and I can write this as psi square to the power j. Okay, so now if you see this, something to the power j by factorial j equal to 0 to infinity is actually exponential of psi square. Okay, so if you see that if you allow these infinite terms to be there in this particular expression, so this part of it is exponential psi square, and there is also another part which is adding to that, which will be much more than exponential psi square. So as a result, what we can say is that this f of psi, it goes like at least like e to the power psi square as psi goes to plus minus infinity if we allow all terms, all the infinite terms in the series. Now, what is the problem if this happens? The problem is that your psi of psi, which is equal to some constant b into e to the minus psi square by 2 into f of psi, that is what we have seen. That is now, this goes like e to the power psi square by 2 because f of psi is e to the psi square, and that goes to infinity as psi goes to plus or minus infinity. That means if you allow this f of psi to go to e to the psi square, then your wave function does not satisfy the given boundary condition. So for psi of xi to go to 0 as xi goes to plus minus infinity, this is our boundary condition. Okay, so this is our boundary condition. So if you want your wave function to satisfy this boundary condition, so f of xi has to be necessarily truncated to some finite number of terms in the power series. Okay, if you don't truncate, then we have this difficulty that the wave function will diverge and we will not be able to. So how do we truncate this? So look at our recurrence relation again. Aj plus 2 is equal to twice j minus epsilon minus 1 divided by j plus 2 into j plus 1 into Aj. Okay, so let's say that let us say that for some j is equal to n, a n plus 2 is equal to 0. Okay, that means after a n plus 2, everything is 0. Okay, how can we make this 0? We can make this 0 by making this numerator 0. Okay, so we get this by saying this 2n minus epsilon minus 1 is equal to 0 for j is equal to n. 2n minus epsilon minus 1 is equal to 0. What does that mean? That means now my epsilon minus 1 is equal to 2 times n. N is some integer. Okay, n is some integer. Or you have energy quantization, which is 2n plus 1. So epsilon is not continuous. Okay, so I may even put this as epsilon n. Epsilon n is equal to 2n plus 1. Now you can see that remember that your epsilon n is actually your En divided by E0, and we have already written what is E0 earlier. So that means the energy eigenvalues of of H, the Hamiltonian operator, are given by En, which is equal to epsilon n into E naught. What is E naught? E naught is h cross omega by 2 into En. En is 2n plus 1. Okay, so that gives us the energy eigenvalues, that En is equal to, I pull out 2 and then write this as n plus half into h bar omega. So this is how we always get, as you have seen in the case of potential problems in one dimension earlier, that we always get this quantization of energies by applying boundary conditions. So here also we wanted psi of xi to go to 0 as xi goes to plus minus infinity, and insistence that psi should satisfy that boundary conditions necessitated that our f of psi has to be truncated, and this is the condition for truncation of f of psi for some n. So your n can start from 0, start from 1, it can start from 0, 1, 2, etc. It can go to any large n. Okay, so this gives you the quantization of energies. Okay, so this is something which is a consequence of energy boundary condition. So this part is fine. Now let's say that so these are energies. Now we can ask what are the wave functions. Or what are called energy eigenfunctions. Energy eigenfunctions. So you see, for example, let's say the lowest value. Okay, so remember that if you fix your n, then j will run from 0 up to n, because n plus 2 onwards is 0, correct? So for example, let's say that we are interested in the ground state. Okay, so ground state, and the ground state corresponds to n is equal to 0. If I take n is equal to 0, this implies my j is equal to 0. So what will be my f of xi? F of xi is equal to simply ag. So what is my psi of xi? Psi of xi is equal to, there is some constant, so I call a0 as constant, into e to the minus xi square by 2. Okay. Now a0 can be determined. So we can determine, we can get a0 by normalization. Okay, we can normalize this one and then get a0. How do you normalize? What is the normalization condition? Because the wave function, the domain of this wave function is minus infinity plus infinity. So you have a0 square into e to the minus xi square p psi. That should be equal to 1. But this integral has got a value square root of pi. So that implies a0 is equal to 1 by pi to the power 1 by 4. So that is your a0. So the ground state wave function, which I will call it as psi0 of xi, is equal to 1 by pi to the power 1 by 4 into e to the minus psi square by 2, with an energy E0 as h cross omega by 2. So this is what you have for the ground state. Now let's look at first excited state. Okay, first excited state. Okay, first excited state that corresponds to n is equal to 1. Okay. Now, if n is equal to 1, then there is no relation between 0 and 1. Correct? There is no relation between 0 and 1, because there is a relation between 0, 2, 4 like that, and 1, 2, 1, 3, 5 like that. So you will see that here j is equal to simply 1. Okay, so that gives you that you have psi 1 of psi, that the first excited state is simply a1 psi into e to the minus psi square by 2. Okay, so you can find out a1 by normalization once again. You get a normalization constant. Okay, and suppose you take second excited state, the second excited state. Let's say n is equal to 2, then j can be 0 and 2. Okay, so that means your psi 2 of xi is going to be equal to a0 plus a2 xi square into e to the minus xi square by 2. But I know that a2 can be written as, so a2 is equal to, you have this recurrence relation, so that is j equal to so a2 can be written in terms of a0 using the recurrence relation, and then you can get this a2, so you can always write a2 is equal to something into a0. Correct. So you can pull out one constant and then represent this. So you will see that if you are, so you can notice that in doing like this, these coefficients. Okay, so your psi n of xi, the nth excited state, can be written as some constant, which I will write as nn, into, there is a polynomial called Hermite polynomial, hn of xi into e to the minus xi square by 2. Okay, so this is this nn is a normalization constant. And you can find out that from the properties of orthogonal polynomials, and you can see that this solutions are written in terms of the Hermite polynomial. So this is essentially what we have with respect to this harmonic oscillator. But note two things here that let me make some of the remarks about this. You see, the first remark is that since your potential V of x is equal to half m omega square x square, okay, so we have a symmetry that V of minus x is equal to V of x. Okay, that means there is a parity symmetry. Okay, whenever you have a potential of this type, then your solutions are the wave function psi n of psi, or whatever psi n of x. So I'm making this a general discussion. So psi n of x should have a definite parity. Should be an eigenstate of parity operator. That means your so parity operator, let's say P, defining on any function of x, is equal to f of minus x. Okay, so this is the action of parity operator on any function of x. Now you say that it is an eigenstate of parity operator. That means your psi n of x should be either even function or odd function, because parity operator has only +1 and -1 as the eigenvalues. Okay, so psi n of x is even or odd function, and this always happens like this. So you can see that all the even index psi 0, psi 2, psi 4, these are all even functions, and psi 1, psi 3, psi 5, they are odd functions. That means your psi 2n of x, psi 2n of minus x is equal to psi 2n of x. And psi 2n plus 1 of minus x is equal to minus psi 2n plus 1 of x. So this is the property of, so whenever you have a potential which is an even function of x, its wave functions or its energy eigenstates will have this property. Now, you can see that this understanding will help us to ask questions like this. For example, if someone is saying that, okay, I have a potential which is slightly different from, let's say it is half m omega square x square for x greater than 0, but it is infinity for x less than or equal to 0. Okay, that means you have a potential which is one side it is like harmonic oscillator, but on the other side it is infinite. So this is infinite. Now you can see that if somebody is asking you what are the eigenfunctions of this eigenstates of this problem, now when you see in terms of solving differential equation there is no difference because the potential is same. But what is different is that the boundary condition for this one is that psi of x goes to 0 as x goes to plus infinity. This is same as the previous boundary condition. The second boundary condition is that psi of x goes to 0 as x goes to 0. Okay, this is because so psi of x is equal to 0 for x less than 0 or less than or equal to 0. Because the potential is infinity, the particle cannot enter into that region. Okay, so psi of x is equal to 0 and wave function has to be continuous, and hence psi of x has to go to 0 as x goes to 0. Now you can see that if you look at your ground state and excited states of the harmonic oscillator, okay, so for 1D harmonic oscillator, okay, so if you plot your ground state psi 0 of psi, okay, let's say this is your psi, that is equal to simply some constant n0 into e to the minus psi square by 2. So this is a Gaussian which is somewhat like this. Okay, and now if you are trying, this is for ground state. Now if you look at your first excited state C psi 1 of psi is equal to some constant n1 into psi into e to the minus psi square by 2. Okay, so you see that there is a graph like this. Okay, so this is your psi versus psi 1 of psi, and this is an odd function as you can see. And the third, let me just draw one more. So psi 2 of psi, okay, So which is equal to n2 into second Hermite polynomial into e to the minus I square by 2. So you can see that this will have a form like this. This will go to 0 only asymptotically. This will harmonize. This is an even function, and so on. Now look at if you look at all these functions, you will see that suppose if I want to have so I want for our this problem, okay, for one-sided harmonic oscillator, we want psi of x to be 0 for x less than 0. That means whatever is there on the right hand, on the x greater than 0 side, should go to 0. So this function, for example, will not go to 0. This function will not go to 0. Only odd functions will go to 0. So for this one, so all psi n of x with n odd are eigenstates of one-sided harmonic oscillator. So we have not solved this problem, but we have a set of solutions, and the set of solutions for this problem is a subset of those solutions. So we can pick them up just by looking at modification to the boundary condition. We are able to pick up some of the solutions as the solutions of this problem. So like that, if you solve one problem, then you can also see that a modification of the potential may actually pick up a subset of those solutions. So that will be easier. So one doesn't have to really solve the problem again. There is no need to solve the problem again. Okay, so this is one another remark that I wanted to make, and so the third remark I wanted to make is with respect to so if you look at large n, okay, so what happens to for large n, okay, for large n, you can see that if you actually plot, see, for example, in this particular case, suppose let's say that you are trying to plot. If you are trying to plot the probability will be something like this for this, and probability for this one is something like this. Okay, so you will see that the probability for large n. Okay, so if you have n to be very large, for large n, if you are trying to ask what is the probability, okay, so the probability will be something like, as you can notice that so you can see that the probability will have some kind of a value like this. Okay, it's not that it is like this. It is going to be like this. That is, there is going to be several nodes, and it is going to be like this. Okay, so if you can think of the probability to be like this, but then if you imagine that this is what we call as mod psi n square as a function of x, for example. Now you can see that if you look at your potential, okay, so if you look at your v of x, okay, so this is v of x versus x. Okay, so classically you can think of defining a probability as, for example, let's say when the particle comes to the bottom of this potential well, the potential energy is low, but kinetic energy is large. So the amount of time it spends at this point is very less. Whereas when it goes to the some kind of depending on the energy, let's say you have some total energy like this, then it can only go up to this point and up to this point, and these are called classical turning points. And it spends more time at turning points because at that point the kinetic energy is zero. So if you define classical probability of a harmonic oscillator, classically the probability, if you define probability as as the amount of time spent at some point x, and you define this as your whatever rho of x. Okay. Then if you plot rho of x versus x, then you will see that it is it will have a formula, and the probability, the wave function mod square for large n will be coinciding with this classical notion of probability, and this is what one calls as a correspondence principle. The correspondence principle. For large quantum numbers, your quantum system will look like a classical, behave like a classical system. And the fourth remark I wanted to make with this is that, as I told you, that if you fix your energy, then there are certain points called turning points. Okay, these are called turning points. Okay, so in this particular picture that I have, let's say this is your potential. Okay, so this is your V of x, and let's say this is your total energy of the system, and these points. Okay, so let us call this as x2, and basically this will be let me call it as xt, and this will be minus xt because our potential is symmetric. Okay, so this xt and minus xt, that is minus xt and xt, are called turning points. So classically, what happens is that if you are thinking of a spring and a mass system on a frictionless table, then it will go up to some point and then return and go up to some point and return. Whereas in quantum mechanics, it is not that it will return exactly same way, because if you see the wave function, okay, if you see the wave function will go to 0 only at x goes to plus infinity or minus infinity. That means quantum mechanically, even if you take the ground state, for example, okay, so even if you take ground state, energy is very small, so there must be turning points at a very nearby region. So if you look at ground state wave function, psi 0 of x, and psi 0 of x is versus x is a Gaussian, that means it will go to 0 only at x goes to plus or minus infinity. That means, let's say if this is your turning point, minus xt and xt. There is a non-zero value of the wave function outside, and suppose if I plot this as mod psi x square, which also looks like this. So this this area plus this area. Okay, so when you do this integration, that will give you that this area and this area together will give you probability that the oscillator is beyond turning point. This is a quantum mechanical origin. Classically, this never happens, but in quantum mechanics, it is possible that you can have a finite probability for the particle to exist outside the turning point. Okay, so this is one remark. And the fifth remark I wanted to make with respect to this oscillator is you can see that the uncertainty in position and momentum, that is when you actually ask what is delta x into delta p. Okay, so this this particular uncertainty, the minimum value of uncertainty principle says that it is h cross by 2. Okay, this is h cross by 2. But if you ask what is the actual value of uncertainty, okay, so that the lower limit is of course h cross by 2, but for a given, the actual value of uncertainty depends on the state. So for a given psi n of x, okay, we can show that this delta x into delta p is greater than, actually this is equal to, you can show this is equal to h cross into n plus half. That means for n equal to 0, that means if you take the ground state equal to 0, the uncertainty is equal to h cross by 2. That means that is the lower limit, the minimum. Okay, but the wave function is Gaussian. The uncertainty is minimum for the ground state. For any other excited state, it will have a higher uncertainty, and that uncertainty can be exactly shown is equal to n plus half into h cross. Okay, so these are some of the remarks I wanted to make with respect to this problem of harmonic oscillator. Okay, I think one last remark I wanted to make is that if you are interested in looking at higher dimensions, that means, for example, in 2 dimensions, you have 2 types of harmonic oscillators. One is called isotropic harmonic oscillator. Isotropic harmonic oscillator. In any higher dimension, you have these 2 types. So we'll talk about 2 dimensions. In which case, you write down this v of x comma y as half m omega square into x square plus y square. So this omega is common to x and y. That is the meaning of isotropic. Now, anisotropic harmonic oscillator has got a potential v of x comma y is equal to half m into omega 1 square into x square plus omega 2 square into y square. So you will have different frequencies for x and y. Okay, and one can do this problem by using separation of variables, and you can get differential equations for x and y separately. So if you have an isotropic harmonic oscillator, then you have your energy eigenvalues will of course have two quantum numbers, n1 comma n2, that is equal to n1 plus n2 plus 1 into h cross 1. And if you have an isotropic, then you have E n1 comma n2 is equal to h cross omega 1 into n1 plus half plus h cross omega 2 into n2 plus. This is just like two distinct harmonic oscillators. Okay. Now you can see that. So let me write down in Dirac notation. The state can be written. So it can be written as n1 comma n2. State is always represented with quantum numbers. So n1 comma n2. So that means now if I have let's say 0 0 is the ground state. I'm talking about isotropic harmonic oscillator. Okay, so 0 0 is the ground state. So the energy E0 comma 0 is h bar omega. Now if you take first excited state, I have 1 0 and 0 1. Both of them corresponds to same value. E10 is equal to E01, that is equal to 2h cross 1. So now we can say that this is a twofold degenerate because there are two states for the same eigenvalue. Okay, and then you have in the next case, that is for 3 h cross omega. So for 3 h cross omega, we have E20 is same as E02 is same as E1 comma 1, which is equal to 3 h cross omega. So this is threefold degenerate. So if you define a quantum number called n, which is equal to n1 plus n2, and write all these energies, this energy you write it as E2, and this you write it as E1, etc. You can see that En is n plus 1 fold degenerate. Okay, the degeneracy of En is, so if Gn is the degeneracy of En, then we have Gn is equal to n plus 1. This is for 2D. So I would leave it as an exercise for you to check, find Gn for three-dimensional isotropic harmonic oscillator. And there is no such degeneracy in anisotropic harmonic oscillator. Okay, so maybe I will stop here, and if you have some questions, you can discuss.
Sir,
Yeah. Go ahead.
sir, if you consider two fermions like of different masses in the harmonic oscillator potential, so what will be? How can we find the first excited state?
Two fermions of what? Different masses.
Different masses.
So a similar question came in CSI net.
So
yeah, I'm asking that reference. Like mass m, another of mass 4m.
So one of mass m and one mass 4m.
M and 4m.
There are four fermions. The question was there was 4 fermions.
4 fermions. Okay.
And in a harmonic oscillator potential, so which what will be the distribution? That the distribution will have the lowest energy, ground state or first excited, downstream lowest energy.
Okay. So you can see that your harmonic oscillator potential will have these energy levels like this. Okay. Now, if there are 4 fermions and their population has to be, there should be 2 in the ground state and 2 in the excited state, first excited state. Correct?
Yes, sir.
Okay. So now you have so the energy of this system is equal to 2 times E0 plus 2 times E1. So that is equal to 2 times h bar omega by 2 and 2 times 3 h bar omega by 2. Correct?
Yes, sir. This is a question I will clarify. They're saying that if there are 4 fermions of 4m mass and 4 fermions of m mass, and there are 3 fermions of 4m mass and 1 fermion of f mass, and 3 fermions of m mass and 1 fermion of 4m mass, which one will have the highest energy?
Okay. So essentially, they want to know this is true, but now what is the dependence of mass here? Your omega depends on the mass, right? Omega is equal to square root of k by m.
Yes, exactly. I followed this principle. Like m will be greater when omega will be less.
Correct. So if you want to have a smallest energy, then you should have
m should be greater.
M should be greater for every particle.
Yes, sir.
So that means all particles should
all
be
4m.
Yeah.
So I got the correct answer, sir.
Yeah.
Sir, one question I was asking in the beginning of the lecture, that there is a capacitor, parallel plate capacitor that was placed on the top of a liquid bath, container containing liquid. So and the capacitor has potential between the plates is V. So the liquid level rises up within the capacitor. It has a height h. So what will the expression for height h? They're saying. So what I did was I calculate the capacitance for parallel plate capacitors with the liquid as dielectric medium and the rest is air or vacuum. So as a parallel combination, I calculate the capacitance and then I calculate half CV square, the electrostatic energy, and then I calculate the force, the force, and then I equated the force with the gravitational force. And then I got the answer for H. Is this the correct question?
Yeah, that's correct.
That was one question, sir. There was another question about double harmonic oscillator, like two potential wells, like double, like parabolic wells. We have to sketch the phase portrait.
Oh, so double well potential.
Double well, like double parabolic.
Okay. So are you saying that it is like this? You're saying that it is like this?
Not exactly, sir. One well has lower depth, another well has higher depth.
Right.
Second one is higher, sir.
Second one is
Lower means the depth is greater.
Right.
Yes, sir. So the face portrait, sir, I considered that to start with the right end. So when the particle is at the top, then it has x is greatest, and so it should be on the x-axis, and then the particle goes down, and when it goes to the valley, its p-value is maximum.
Correct.
So x decreases and p goes up, and then again p goes down and x also goes down, and then it reaches a minimum, and then x goes to negative, and p goes up. That's how, sir, I sketch click the option, sir.
Yeah, I think it's fine. Let's assume that this is your so this is x greater than 0, and this is there some x greater than 0, less than 0 in the graph?
Yes, sir, probably.
Yeah, I think your arguments are correct. So I hope you got the right.
Okay, sir. Like there was other questions. I don't. Yes, there was a question on the Green's function, like of the Heaviside step function as the forcing function. Heaviside step function, and we have to determine the Green's function for it.
Okay.
That was the question. Another question, and then another question was like nonlinear differential equation. That is, I can remember.
What about statistical mechanics? You are able to answer questions?
Yes, sir, there was a question on the per particle internal energy.
Okay.
Like there was p square over 2m plus lambda x to the power 4. Okay. The Hamiltonian was. So that should be 1 by 2 kBt plus 1 by 4 kBt.
Yeah.
So 3 by 4 kBt. That should be.
Yeah.
Equipartition theorem. So others can remember other questions. I remember all these.
Okay. But anyway, I think it is too much work on the memory to remember questions. I think you should probably, when the examination is going on, you should not try to remember the question, because that is an additional load on your memory.
Yes.
Sir.
Yeah.
Sir, I have a general question, sir. So we have two types of formalism in quantum mechanics, right? Wave mechanics and matrix mechanics. So how is matrix mechanics different, or how will be the approach in solving problems in matrix mechanics?
Actually, when Heisenberg developed quantum mechanics, he used this matrix method. But later, people have shown that whatever you do from Schrodinger, wave mechanics and matrix mechanics are equivalent. And whatever method that you have done using these ladder operators is actually a sophisticated matrix mechanics later developed by Dirac using these infinite dimensional operators. So right now, your matrix mechanics is same as that operator method. And that is what you do in angular momentum theory. That is what you do in harmonic oscillator. And when you go to second quantization, these methods are more useful in terms of operators. Okay, so there is no difference. They are equivalent, but only thing is some problems are. So, what is the advantage of this wave mechanics is that when you have potentials which are kind of, you have a classical system and you want to study corresponding quantum mechanical system, then these things will be slightly more closer to your classical. You want to have some classical connection always, then you should do this in the wave mechanics. But for example, if you go to properties which don't have classical analog like spin, etc., then you have to only do operator mechanics.
So I wanted to know if my comparison is correct. Suppose if we are representing, for example, if you are representing a psi as a sin x, and if you are alternatively, if you are taking a list of all the maybe the points of sin x, are those equivalent, or is it like this list is the analogy of this matrix mechanics here?
I'm not sure I understood what you said, but if you have a function and then you have all points in the function, are you saying that if you write the function, it is like what you do in wave mechanics, and if you take all the points in the function, it is like elements of the function? Is that what you are saying?
Yes, sir. Yes, sir. Exactly, sir.
Yeah. So it's not exactly like that. See, if you can remember that, I can say that. So as I said, that let's say that you have some psi of x. Okay. Now in position basis, that is, if you are considering a basis like this, okay, in terms of this basis, this is like a component of some ket psi along x. Okay, that is what we wrote this psi of x as projection of psi along x, right? When we talked about the postulates, we discussed this one. So this is like components. Okay. So in that sense, if you may call this psi ket as this is called a ket vector in general, or a ket vector sometimes. So now this x is every point in the x-axis. So you have minus infinity to plus infinity. So you take a point here, and then you define an x. You take a point here, then you define that as x prime, and so on. So at every point, you have a component. So in that sense, if you take your psi of x, then the value of psi of x, suppose if you plot this psi of x as some kind of a function like this, now this is like one component. This is like another component. This is like another component. So psi of x, the values of psi of x are like, so values of psi of x are like components. They are components of infinite dimensional vector set. So this is what is the interpretation. So it is still a vector. The values of the function will be like components of the vector. Now, the matrix corresponds to an operator. Okay. Suppose I have an operator A, and then I can think of this operator as a matrix element. In the sense, suppose if I take some psi, and then I take some phi, okay, okay, so I think let me write it like this. I choose some basis, phi n, okay, because to write matrix, to write an operator as a matrix, I should choose some basis. So let's say I choose some basis like this, and then I write phi m, a, and phi n. Okay, so this as a m n. Okay, and this is going to be m and n are infinite. This n is actually It can go from 0, 1, 2 up to infinity. So this is an infinite by infinite matrix. So all operators can be written as matrices, and all wave functions can be written as vectors. All of them are infinite dimensional. Okay, I hope this would clarify.
Yes, sir. So further a question, sir. Sir, if we are integrating within the limits under consideration, and if you are taking psi star psi, and suppose we are considering maybe an equivalent a row and column matrix representations. So taking the dot of this first is it equivalent as taking this integral psi star psi?
Yeah. But, I mean, when we first developed this this inner product, I think I discussed, and if you remember, I also told you that this was discussed in R. Shankar's first chapter.
Yes, sir.
So what I am saying is that you could write your psi, and then you could use some phi. Okay, so this is like you have if at some finite level. Okay, at some finite level, you can say that you have phi 1 star, phi 2 star. These are like elements, and then this is like psi 1, psi 2. These are like elements. Then you write this as sum over I. Okay, so phi I star into psi I. You can write it like this. But what happens because this goes to infinity. Okay, this if you take phi is equal to psi, for example, you take psi itself, then what happens is this is sum over I, psi I mod square. Now this is positive for this is positive for all I. So there are infinitely many positive numbers. When you add it, this whole thing will go to infinity. That diverges. Now if you don't want such a divergence, you multiply that with some small number delta, where this delta can be written as an xi minus 1. Okay, so as n goes to infinity, this delta goes to 0, so this product will remain constant. So this can be written in the limit n going to infinity and your delta going to 0. This becomes your function phi star of x into psi of x dx. Whatever is the limit. Let me put it plus infinity. But whatever is the limit, if it is 0 to L, you have to put 0 to L and so on. So this is same as that, except that we have to define it in such a way that it doesn't go to infinity.
Yes, sir. So this was posing all the confusion for me. I was not considering this this little delta while doing this operation.
Yeah. So I think if you look at the first lecture of our postulates, I think I talked about it in detail. And if you don't have that, you can look at R. Shankar, Quantum Mechanics, first chapter.
Yes, sir.
So
now it's clear, sir.
Yeah, we also discussed this matter.
Thank you, sir.
Sir, I remembered another question from like statistical mechanics that came in CSIRNet, that we have two containers, one of volume V1, one of volume V2. With ideal gas, one has N1 particles, one has N2 particles, and with a partition in between. And then the partition was removed. Okay. What will be the pressure after the partition was removed? So I approached the problem like the extensive variables are V and N. So the after the partition was removed, the total volume will be V1 plus V2. And total number of particles will be N1 plus N2. So I wrote P into V1 plus V2 is equals to N1 plus N2 kBt. So P is equals to kBt times N1 plus N2 by V1 plus V2. So is it correct?
Yeah.
This was one question, and another question for quantum mechanics came that if potential was given that is equals to k by r square, we have to find the scattering amplitude. How does that depend on the momentum transfer? Q.
So that you can use Born approximation.
Born approximation, yes, sir. That came 1 by q square. I know others, like someone, others have found the same answer or not.
Yeah, 1 by q square is correct.
1 by q square, yeah. For 1 by r square, I got 1 by q square.
Yeah.
And so another question came. I told you that the finite potential well and half infinite potential well and infinite potential well, which will have, and we have to arrange in the descending order the ground state energies.
Yeah, I think see, both sides infinity will have highest energy.
Yes, sir. Both sides, and then the half infinite.
Yeah, then both sides finite. Yes,
both sides finite. Yes. I chose that option. Another was like there was 3-level system with like 1 to 0, 1, 2, and A20 is given 1.2 into 10 to the power minus 8 second inverse. So Einstein's coefficient. A21 is 1.2 into 10 to the minus 8 second inverse. A20 is 8 into 10 to the power 7 second inverse. So what will be the average lifetime of spontaneous transition of the second excited state? So that will be 1 by A1 plus A2. Actually, at first what I did was A1 plus A2 by 2 because it was average, and then taken the reciprocal. Then I changed it. Actually, did 1 by A1 plus A2.
Yeah.
So that
but I'm surprised that you are remembering these numbers.
I actually remember two options only. Option B was 1 into the minus 8 second.
You are remembering these numbers also, no? That A12, A21.
Yes, sir, because if we add them, we get 2. 2 into the 8. So that I did, sir. I don't know others got the same answer or not.
Anyway, now you don't have to do some postmortem of that. Leave it for some time.
Yes, sir. Okay, sir. Thank you.
Okay. So if no other questions.
Sir?
Yeah?
It's a small doubt, sir.
Yes,
sir, for that two-dimensional harmonic oscillator, how to write the wave functions?
Yeah, so actually we are doing this problem almost like two one-dimensional things only. So for example, if you are, well, let's say you have psi 0 of x comma y, ground state, so you have some constant n0 into e to the minus x square plus y square divided by 2L square. That L is basically that characteristic length, okay, which is going to be same in this case. This is for isotropic. Okay. And if you have anisotropic, so psi 0 of x comma y is equal to from n0 into the minus x square by 2L1 square minus y square by 2L2 square, where L1 is equal to h cross by m omega 1 and the square root, and L2 is equal to square root h cross by m omega. And you can write down psi wave function Okay, this I should write psi 0, 0 of x. Now psi 1, 0 of x comma y will be equal to n0 into x into e to the minus x square plus y square by 2l square. Because there is 1 with respect to first one. And psi 0 comma 1 of x comma y will be, maybe I call it as n1. n1 into y into e to the minus x square plus y square by 2l square. And psi 1, 1, if I want to write, this is not, of course, same energy, x, y, then this is equal to some n2 into xy into e to the minus x square plus y square divided by 2l square, and so on.
So we are multiplying the one dimensional.
Correct. So your psi of x comma y is equal to, you can write it as phi of x into chi of y. This is how separation of variables we do, no?
Yes, sir.
So x and y are independent, so we can do separation of variables. It's like writing two different. So that's why there is nothing new in solving this higher dimensional harmonic oscillator, except that the new concept is this degeneracy.
Yes, sir. So one more thing, sir. If the particles are maybe like here we have taken spinless, it doesn't matter about the energy and wave function whether they are fermions or bosons, right? Like except for the spin part.
Correct. So if they are fermions or bosons, it doesn't matter, because it is like, see, the point is something like this. If you have, everything depends on your Hamiltonian. As long as your Hamiltonian is this p square by 2m plus half m omega square x square, these energy levels are what you will get. Okay. But suppose you have more particles and they have spins, then you are only populating them according to Pauli principle if they are fermions, or populate them as such if they are not fermions. Okay, that is only population. But there may be a situation where if those particles are interacting with each other, then there will be additional terms here, right? And this interaction may also be spin interaction. That means there are going to be some spin degree of freedom inside the Hamiltonian, in which these levels will not be same. These levels will get modified.
Okay, sir. And sir, this spin thing, like you have taught us in statistical mechanics, this Bose-Einstein Bose-Einstein statistics. How here the spin is connected to the statistics? Like in the class you told, but I couldn't understand properly. Like the spin statistics connection.
Yeah. Yeah. So that, see, if you are asking how, I have to say either this question how has answers at two levels. One is a proof. I have to give a mathematical proof. Okay, and which is not available at this moment. You have to actually get this proof from quantum field theory. Okay? And second thing is, it is like that is like nature. Okay, so nature establishes that connection. Okay, that is why I mentioned that it is spin statistics connection. But one can mathematically prove that as a spin statistics theorem in quantum field theory. Okay, the two important theorems in quantum field theory is, one is called CPT theorem, then this is called spin statistics theory. Okay, so this connection between spin and statistics is one of the fundamental nature of the particles.
Okay, sir.
So one last question I remembered that this is from classical mechanics. Like there's a disk rotating with the angular velocity omega, and we are placing a ball of radius a at a distance r from the center of the disk. What will be the linear velocity of the ball? That is a frictionless disk.
Okay.
A frictionless disk rotating with angular velocity omega. We have to place a ball of radius a at a distance r from the center of the disk. What will be the angular, the linear velocity of the ball? Frictionless disk. There are four options. Like I first tried with r dot r cap plus r theta dot theta cap, but then it's a frictionless, no? So there will be no force on the ball, so it will be 0, I think.
What are the options you have?
0 was on the options. Other was like minus a omega theta cap plus something, like I don't remember, sir. But sir, I think it will be 0. Will it be 0, sir? Because I first tried with r dot r cap plus r theta dot theta cap v equal to, but like there was no, it was the radius of the ball that will not be included in the calculation, no?
Yeah.
So all of the options, rest of the options had a.
Yeah, I think that's correct.
0 will be the correct answer, sir.
Yeah, I think so.
I also think so. 0 will be the correct answer. Okay, sir. That questions I remember. I don't remember any more questions.
So many you remember anyway already.
Okay, sir. Thank you.
Okay. Ashley?
Hello, sir.
Yeah, can you close?
Yes, sir. Yes, sir. Good night, sir.
Okay, good night.
So will there be any class on Wednesday?
Yeah, so actually there seems to be a big cyclone here, and there is a lot of I don't know if there is network we can have class. Exam, as Shruti told me, we have postponed to next Wednesday or test. But if I don't know if power will be there, or because it is supposed to be crossing the landfall should be between Pondicherry and Chennai. So it looks like where I am staying is where the cyclone is coming. So if power is there, then we can have. Otherwise, we will not be able to do the class.
Okay, sir. Thank you, sir.
Okay.